right, here in part 5, we're now going to derive the J flip-flop state equations. We just finished deriving the D. Now we'll create then our sequence detector of 110, that finite state machine, using JK flip-flops. Again, we need 2 flip-flops for our finite state machine. In this case, we'll be using JK. We'll have to develop state equations for Q0 naught and Q1 plus. We're going to have to add 4 columns to our state table, J1, K1, J0, K0, because remember, a J flip-flop has 2 inputs, J and K. So for the flip-flop that represents state Q1, we have to decide what the inputs to J1 should be and the inputs to K1. For the flip-flop that represents Q0 in the next state, we have to determine then what the inputs are to J0 and K0. We use the characteristic equation, right, or we use the excitation table to do that. Right. What we're going to do then is, like I said, I'm going to show you parts of the state transition table. The first thing we're going to take a look at is, here are 3 inputs, present state of Q1, Q0, and X. Our next state of Q1, so Q, and then we said then we have to decide what the values must be of J1 and K1, then based on Q1 in the next state and Q1 in the present state. So remember, I've got the JK flip-flop excitation table. When we derived those, we said the values of J and K here were dependent on Q in the present and Q in the next. Right, so if we look here, when Q1 is a 1, so this is the first line of that state table. Right? When Q1 is a 0, and our input, so we said here, right, when our state is S0, and our input X is a 0, our next state was S0, that's that first line of the table. We look here at Q1, we say, well, Q1 in the present is a 0, Q1 in the next is a 0. So Q in the present is a 0, Q in the next is a 0. That means the value of J should be 0 and the value of K should be a don't care. Remember, we're representing Q1 with the inputs J1 and K1. So J1 is a 0, K1 is a don't care. Right. We can start filling in other lines then on the state table in the same way. The next line on the state table was when we were in state S0 and our input X was a 1, our next state was a 0. Right. Well, we'll look here at this line where Q1 is a 0 in the present, Q1 in the next state's a 0, right? Well, there's no transition, but once again, if we were to go to the excitation tables to figure out then what values to fill in with J1 and K1, because the values are shown here, but you're creating these tables and deciding this, right? Well, once again, present is 0, next is 0. Present is 0, next is 0. That means J must be a 0. We don't care about K. This line of the state table, the next line, when we're in state S1 and our input X was a 0, we said our next state was S0. So Q1 in the present state's a 0. Q1 in the next state's a 0. Well, it's the same thing we just had before. So J1 is a 0. K1 is a don't care. Right. The next line in the state table then, right, is Q1 in the present state is a 0. Q1 in the next state is a 1. So we go to the excitation table and we say when the present state is a 0 and the next state is a 1, this line, J must be a 1 and we don't care what K is. So our value for J1 was a 1, our value for K1 is a don't care, right? Remember, J1 and K1 are unknowns that we're filling in. Right, next line in the truth table, 1, 0, 0. Right. Well, when Q1 is a 1 in the present state, for this particular line of the truth table, the next state is also a 1. So we go here, Q in the present is a 1, Q in the next is a 1. This is, we don't care what the value of J is, but the value of K must be a 0. So what we fill in here for J1 is a don't care, K1 is a 0. Notice the very next line of the truth table, right, where we're in state S2. Our input X is a 1, our next state is a 1, or is S2. So Q1 in the present is a 1, Q1 in the next is a 1. J1 then is a don't care, K1 is a 0. It's the same thing. All right, we've got 2 more lines of our table. Right, the next line, right, 1, 1, 0. Well, Q1 is a 1, Q1 present, Q1 in the next state is a 0. Excitation table, Q present is a 1, Q next is a 0. That says the value of J is a don't care, the value of K is a 1. So the value of J is a don't care, the value of K we say is a 1. The last line of the truth table is the same thing. Q1 in the present is a 1, Q1 in the next is a 0. We don't care what J is then, we care what K1 is, right? And so now here's everything all together, right? Here are all 8 line inputs of our truth table. Here's Q1 plus. For Q1 plus, we use that to derive these values of J1 and K1. Right? These are the input values that must be sitting there waiting on J1 and K1. We need to do the same thing then for Q0. We need to figure out what the values of J0 naught and K0 will be. Right. So similarly, we start going through the truth table. Right, we're going to use the column Q0 in the next, Q0 in the present, because and then we're going to decide what the values of J0 and K0 should be. So Q0 in the present, right, this is the first line of the truth or the state table where our inputs are 0, 0, 0. So Q0 present is a 0, Q0 next is a 0. So Q present 0, Q next 0, J must be a 0. We don't care what K is. That's where these come from. Right. And we can do the same thing then for the rest of the table. So what I've done is here, instead of showing every line, I'm just showing the columns for all 8 states, present, next, right? So I can then compare the two. That's what we've been doing, right? And here are values of J and K. Now we end up with a state table that looks like this. Here are all of our 8 possible inputs. Right here is where we showed what the next state was based on these inputs. Here is where we derived J1, K1, and J0 for these flip-flops to generate those next states. Z is still the same as it was, right? Z is not at all dependent on the flip-flop we use. That won't change. What we need to do now is we have to derive 4 equations, right? We need to derive an equation for J1, K1, J0, K0. So we call these state equations, right, for our J flip-flops. Right? Each flip-flop has these 2 inputs, right? We're going to we'll name one flip-flop Q1. We'll attach J1 and K1 to that. We'll name another one Q0. We'll attach J0 and Q0 to that. We can use a K-map, right? Each one of these then here, we're going to think of J1 as an output. Right, we want to derive an equation for J1 that's dependent. J1 is a function of Q1, Q0, and X. K1 will be a function of Q1, Q0, and X. Right. So J1, right, so here I pulled the data from J1. Here are our inputs, Q0, Q1, and X. Right, we created a K-map. Right, here's mapping the 0s and 1s over here, mapping the don't cares. In this case, we could use, if we solve for a 1, we can use a don't care with this to derive an equation, right, of Q0 and with X. Right. That circuitry then, Q0 and with X, and this X is our input X, this is not a don't care, would be this AND gate here. What we'll do is we'll go ahead and derive the expression for K1. I'm already showing the circuit here. Let's see where that's derived. Then K1, right, here's we treat K1 as an output. Here's our input. So, right, we then K-map for K1. That's a lot of Ks. If we could solve for 1s or for 0s, either way. Here I chose to solve for the 1s, try to use the don't cares to form a group of 4, and got a reduced expression that said K1 is just going to be equal to K0, which actually then here, notice this is just Q1 and with Q1. Actually, that is an old diagram. That is a mistake. So forget that value for K1. That's a picture I can't easily get rid of right now. So all right, just pay attention to this for J1 here. K1, we said, was equal to Q0 naught. This should be our circuit here. All right, this is our Q1 flip-flop, right? I named that wire Q1 coming out of there. Provide a NOT gate to then create the signal Q1 NOT when we need that in an expression. Right. We're going to do the same thing now for J0 and K0. So for J0, we take this column for J0, right? Here are our inputs. K mapped it here. I decided to solve for the ones. So here we had this group of two, right, that I could use don't care for, and then I use the don't care with this one, right, to come up with this expression of J0 is Q1 and with X naught, or with Q0 naught and with X. So here is our flip-flop then Q0. Ignore the Q1 not down here. That is, yep, I'm going to have to fix those pictures. Sorry. I really need to fix those pictures, don't I? I will upload the correct pictures in your lecture notes. All right, so J0 then is, right, this expression here. Here are AND gates for these two. Here are OR gates. Ignore the Q1 flip-flop. Similarly, right, finally we created an equation for K0. Here's K0's output. Right, we can map that. Right, K0 in this case is going to be equal to X naught or with Q0 naught. So group of four here, group of four here to have that reduced equation here. So X naught or with Q0 naught. So this is our Q0 flip-flop in our circuit schematic. And here's Q1. This circuit is correct here. This circuit is correct there. Those intermediate circuit pictures were not correct. I need to fix that. All right, but so once again, in case you've lost track, our finite sequence detector of 110, this is how we implement it with a JK flip-flop. Once again, now output Z. So here I've shown output Z. Z is just Q1 ANDed with Q0. Right? It does not depend on the flip-flop type, just the flip-flop outputs. Right? That will be the same for whether we use a D, a JK, or a T. Right? So this is what the circuit looks like. Here is the Q0 output, here is the Q1. Here are your J1 and K1, your J0 and K0 outputs. So this is the circuitry we need to make to then detect that sequence 110. You can go back and look at the D flip-flop, compare that implementation. Right? One may use more gates than the other. It may be a bit of a toss-up. Right? We're not concerned about efficiency in this case, like which is better, D or JK. Typically, right, which one uses less resources typically turns out to be the better of the two. Right now, we're just learning to derive these. Finally, now, our next section of our lecture will then derive how do you then create the same state machine with T flip-flops. Right, sorry about the intermediate errors in the intermediate slides of the circuit. I will correct that.